In the last chapter, we focused on the reflection of light. Now we're going to be looking at what happens when light passes from one transparent medium, such as air, into another transparent medium, such as water or glass. When an incident light ray strikes a smooth boundary between two transparent media, such as air and water, you will see two things happen. Part of the light will reflect, and this reflection will obey the law of reflection, where the angle of incidence, which is labeled as theta 1 here, is equal to the angle of reflection, which I'll label as theta 1 primed. Typically, in this kind of scenario where you have a light beam that comes through here, maybe about 5% of that light will reflect, and then 95% of the rest of that light will be transmitted into the new transparent media, such as this water. The beam that is refracted in this new substance is called the refracted ray. And we'll see a couple things as it moves into this new medium. There's a few changes. First of all, you may notice that the ray of light changes direction. And this is because of the change in the speed of light. Light slows down as it moves from air into water. Furthermore, the wavelength in the new medium will also change. The one thing that doesn't change from each of this two different media is the frequency. We'll get into the specifics in a minute. Let's talk about index refraction now. Earlier in the previous chapters, we learned that light travels in a vacuum at the speed of light. We labeled the speed of light as c, and the speed of light in a vacuum is equivalent to 3.0 times 10 to the power 8 meters per second. So that's the speed of light in a vacuum. Regardless of the wavelength or frequency, all electromagnetic waves travel at that speed. However, when light travels into clear, transparent substances such as air, water, glass, plastic, light slows down. And this is due to the process, the fact that light, when it enters the new medium, it gets absorbed and re-emitted, and it slows it down. To qualitatively describe how much the light is slowed down, we use something called the index of refraction, which we label with a little letter n. Now, the index of refraction is equivalent to the ratio of the speed of light, which is denoted with a c, all over the speed of light in that particular medium, whether it be air, or glass, or water, etc. By definition, the index of refraction in a vacuum will be exactly equal to 1, because you'll be taking the speed of light in a vacuum divided by the speed of light in a vacuum. That's going to be 1. Now, as light travels into different transparent media, it slows down. And the more it slows down, the greater the index of refraction. So, if we go into air, for example, it doesn't slow down that much. The index of refraction for air is 1.0003. If you go into, say, water, the index of refraction is equal to 1.33. It slows down quite a bit. Or if you go into, say, some different types of glass, and they'll all have a variety of indices of refraction, it'll be about 1.5. And you can get a variety of indices of refraction, and they actually vary for the frequencies of light too. So as you go into glass, red and violet will have even their own index of refraction. But we'll get into that later on when we talk about dispersion. You may notice that these indices of refraction that I've been writing down have no units, and hopefully you realize that. You've got a meter per second on top and a meter per second on the bottom, and they're going to cancel out. So the index of refraction is a unitless quantity. You may also note that the index of refraction is typically, I should say, greater than 1. Not really always. And the reason why we would say that is really due to relativity, that nothing can go faster than the speed of light in a vacuum. So as light travels in different media such as air, water, or glass, it'll always slow down. So your index refraction should always be a value that is greater than 1. However, if you kind of do some searching on the internet, you'll find that there are examples where n is actually less than 1. But this is kind of beyond the scope of the course, and I would say that if you ever end up with index refraction that is less than 1, you're probably making a mistake. So let's return to our discussion of refraction. What is refraction? Well, it's a bending of a wave that is due to a change in the propagation speed. And this, by the way, applies to not just light waves. It also can apply to any wave. Anytime a wave moves from one medium to another medium where the speed of that wave actually changes, then it will actually bend. And that bending is called refraction. Now let's take a look at it a little bit more closely so we can describe things like what happens to the wavelength, for example. To help our understanding of what happens to the wavelength as it goes from air into water and it refracts, let's draw the wavefronts. Let me show you the wavefronts for the incident ray. These purple dashed lines are what we call wavefronts. And the distance from one wavefront to the next wavefront is called the wavelength, which I've labeled as lambda sub 1 for the wavelength in this air media. As the light travels into the new medium, water, we find that the wavefronts get closer together. And so therefore the wavelength in this water medium is now smaller. In order for the wavefronts to remain in sync with each other, the ray must bend towards the normal as it adapts to the new change in speed. So we see that the wavelength decreases as the speed decreases, but there is one quantity that does not change, and that is the frequency. The frequency in this medium and the frequency in the new medium is the same. So frequency 1 and frequency 2 remains constant in any kind of refraction. So as the light wave moves from air into water and slows down in speed, the wavelength decreases while the frequency remains constant. Since the frequencies are equal to each other and frequency equals speed over wavelength, you could rewrite the left and right side of this as v1 over lambda 1 equals v2 over lambda 2. And then looking at our definition for the index of refraction where n is equal to c over v, if we were to rearrange for the velocity, we would get c all over the index of refraction n. So let's replace that in here. So if we were doing v1, then we would be doing c over n1. Or v2 would be c over n2. So now this relationship now becomes c all over n1 divided by lambda 1 equals c all over n2 divided by lambda 2. Then the c constant cancels out from both sides. And rearranging, we'll get n1 times lambda 1 equals n2 times lambda 2. And this is a really helpful relationship. Later on, we'll be using this with thin film interference. The law that relates the angle of incidence theta 1 to the angle of refraction theta 2 and the index refraction n1 and the index refraction n2 was formalized by the Dutch scientist known as Snell. And so we have Snell's law, and this is one of your AP formulas, n1 times sine theta 1 equals n2 times sine theta 2. It's also written this way in terms of velocities, and this relationship we have just derived, which is very helpful as well. After this video, you can practice using Snell's law and the relationships that we just came up with doing example 1. But before you do that, let's just go over a couple key conceptual things regarding what happens to the wave as it goes from an index refraction that is small to an index refraction that is larger. As it moves from, say, a light travels from a less dense medium like air into a more dense medium such as water or glass. Here's an animation I found on the internet that helps summarize some key conceptual ideas. you can see we have the reflection and refraction that is occurring between this air in the black area here and the glass, this gray area media. Now, as the incident ray comes in, we have a reflected beam, and the angle of incidence and the angle of reflection are equal to each other. No matter what you do to this angle of incidence, the angle of reflection will always be the same. Now, you can see, no matter what, as I change the angle of incidence and angle of refraction, will always deviate towards the normal. So it will bend towards the normal. So when you go, it's a good rule of thumb, when you move from less optically dense to a more optically dense medium, the ray will deviate or bend towards this normal line. All right? Or you could also coin it as you move into a slower speed, as you go in from air into water or glass, the light's going to slow down, and that light beam, the refracted beam, will bend towards the normal. Now, if you go from, say, glass to air, I'll move on to the next scene here, then you'll see you're going from more dense, which is like n equals 1.5, to less dense. Now the beam bends away from the normal. Sometimes you get these kind of conceptual questions asked on the multiple choice where you have to rank indices of refraction. Also note what happens if I were to increase this index of refraction to a higher or lower levels. If I make the index of refraction bigger and bigger, max it out here, you can see I get more bending occurring. As the index refractions of the two substances approach the same values, eventually that line will just basically not refract at all. But right now it's still bending because it's 1.25. Furthermore, if you were to send the incident beam at an angle of 0 degrees, then you do not get any refraction at all. So refraction has to occur at a non-perpendicular angle to the surface. Here's another animation that you may want to play around with. I've placed this up on Blackboard for you guys to practice with. Now look, if I were to make all of these the same index refraction, the beam doesn't deviate at all. If I were to change this, so this is air, this is now, let's keep this at air, but now let's change this to say water. So we'll move this to like 1.33 or something around there. So now you can see the light beam comes in, bends inwards as it comes into the water, then bends back outwards as it returns back into air. And if you were to look at this beam here, right here, and compare it to the incoming incident beam, these two will be parallel. That's why when you look, say, through a glass pane window, you're not going to see any of that bending occurring like you would see with a pencil in the water. That's because the light beam will bend back parallel to what it was. Now, sometimes on the multiple choice questions, you get questions where suddenly the beam bends more, and you can see bends inwards and bends inwards a little bit more, and so then you're supposed to rank the indices of refraction and realize that N3 would be the greatest, then N2, and then N1. So you get all sorts of kind of variations you can kind of play around with it. Maybe make this 1.1 and this 1.4, and then you're supposed to kind of rank the indices of refraction. So you can see here it's going to, you have to kind of compare them. You see that it goes from this ray into this ray. It's going to be bending inward, so you know that N2 is greater than N1 because it's bending inwards towards the normal. And then if you look at between theta 2 and theta 3, it's bending away now, so you know now in this case that N3 is less than N2. Then to compare the first one and the second one, you have to see if they're parallel. If they were parallel, then they would be the same. So there's a bunch of arguments that you can kind of play around with this, but just wanted to point out because sometimes this comes up in the multiple choice questions as kind of like you see this picture here and they tell you how the angles are related to one another and you have to rank the indices of refraction. Okay, that's it for our discussion of refraction, index of refraction, and I think you're ready to try some problems now.